Good afternoon, class. How lovely for you to come. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Not so bad. Pretty good turnout. I guess I'm a little late, so we can go ahead and get started. Whose iPhone, by the way? Who's this iPhone person? Yeah, thumbs up person. Who are you? I'm going to unmute you. Now tell me. Who are you? Who are you? Okay, forget you, man. All right. Let us share screen. I'm going to share with you my PowerPoint. By the way, don't touch this PowerPoint. It's so fresh that the ink will run if you touch it. Just finished it this morning. Bringing up my chat so we can have a chat. Organizing my desktop. And I think we're ready. Okay, so we left off yesterday, or 2 days ago, I should say, on this slide, slide 24, and this was talking about the conversion extension that happens during gastrulation of the Xenopus. The Xenopus dog. Are you the Xenopus dog? Come here. This is the Xenopus dog. The Xenopus dog wants to go out. I'll be right back. Go get him. Okay, sorry about that. Okay, so now we're going to finish off this semester. I feel bad because I feel like we didn't go over that much material, but it was pretty intense stuff. It was a lot of work getting it together anyway. So today we're going to finish talking about gastrulation in the chick and then neurulation, which is again morphogenesis. So we're talking about changes in cell shape, cells moving, convergence and extension, all those things. So the primitive streak, if you remember from way back chapter 3, you've got Henson's node, which then the primitive streak starts there, and it goes from posterior to anterior. So that action of moving from posterior to anterior is all about convergence and extension. So here you can see in slide 25, cells are coming from laterally towards the center and then moving forward. So they're converging and extending forward, and that's how the primitive streak extends. And as that is happening, here's a cross section through the streak. As that is happening, you've got this, we've talked before about apical constriction. So this is the apical side of the embryo at this point, the upper portion. And so you've got actin and myosin there that can contract. So you've got some tension on the top that's kind of pulling things together there. And at the same time, you've got cells coming forward like this. And when those cells hit the middle of those cells are coming in, and when they hit the middle, they undergo the EMT transition. So they're going from these epithelial cells into mesenchymal cells. And that transition involves, like we talked about before, adherens junctions that are letting go. Normally you've got these tight adherens junctions, which I think are these little blue dots here that are holding the cells together tightly into that tissue. They let go, and now you've got cells that can start to crawl. Two things going on, letting go and crawling. And the crawling has to do with FGF. FGF is stimulating these cells to crawl. So let me make sure, I'm just pulling my notes up to make sure I haven't forgotten something. So primitive streak formation involves convergence and extension, making the streak, and that is being driven by apical constriction. which is pulling the cells to the center. The side of the epiblast, the side of the right? Cells change shape. So as they get to the middle, they become wedge-shaped. You can see the shape change here. And again, that's apical constriction. They lose their junctions and let go. Oh, another thing that happens here is, remember our basal lamina. You know, it's funny, I've been talking about similar things in this class in cell biology, and I don't remember if I talked much about basal lamina in this class, but this yellowish orange thing here is your basal lamina, and that's a thick protein layer between epithelial cells and cells inside the epithelia, and that breaks down. Proteases, no doubt, breaking that down so that the cells, when they start to move, can move in, so they're not getting stuck on that basal membrane. And by the way, if you're in cell biology too, and a lot of you are, notice how this is basically a cell becoming malignant, right? It's letting go of its cells, it's starting to crawl, and it's breaking down the basement membrane and invading other tissues. So you can see how easy it is for some cells, like epithelial cells, to become cancerous, because they've got that program already in them. They just need to activate that program. What activates the program? FGF, right? And FGF is a receptor tyrosine kinase, which activates MAP kinase, RAS, MAP kinase, any of those proteins that get activated turn this program on. So that was cell biology. If you're not in cell biology, you got a little bonus today. If you are, then I feel sorry for you. Okay, so then the surface epithelium, the cells that don't go in, then become epidermis, okay, or ectoderm, I mean, which then will be neurulated into neural ectoderm or stay epidermal ectoderm. But anyway, the ones that don't ingress then remain as ectoderm. The ingressing cells, as they convert from epithelial to mesenchyme, also become mesoderm and endoderm. I think at the time we called them mesendoderm back in chapter 3. So basically they are somewhere between, and they can go in either direction depending on how they get stimulated once they're in. And once inside, the cells migrate into place under the influence of FGF, which keeps them motile. So I throw out Hox genes here in the notes because, you know, we're looking at a cross section here in this figure. And in that cross section, there's a specific set of Hox genes that are activated, and those cells will go anterior and lateral, and that will all be patterned by those Hox genes, as we talked about previously. So each slice then will have a different patterning based on which Hox genes were activated when those cells went through. Okay. Okay. Any questions about that gastrulation? No questions? Comments? Can I get a thumbs up or an amen or something so I know you're still out there? Peoples? Adya, thank you. Any other people want to say hello? Nothing? Brady Vassar. Can always count on Brady Vassar. Yes, sir. Leo Lee gives me an amen. Catalina gets a thumbs up. Brian Perez is sleeping. Emily doesn't care. She's going to be a pharmacist, and this will have no effect on her life from here on out. I can't do anything to Emily at this point, by the way. I could fail her in this class and she'd still be a pharmacist. And that's what upsets me. I hate when I lose control. Okay, let's move on to slide 27. And we're going to start talking about notochord formation. Where is this in my notes? Hang on a second, I just need to. I did that in class once years ago. Students were annoying me and I went, and this one student from Palestine, she said, that's a letter in my language. Those Middle Eastern languages have a lot of throat. Okay, there it is. Sorry. Found it. Notochord. Notochord. Ooh, Brian Perez is awake. That's good to hear. Still, I'm doubting though. I know I can see you're awake now. I don't know if you were awake before. Okay, notochord. So we've talked about notochord quite a bit. It's a long rod that's underneath the right underneath the surface, and it induces neurulation. So it induces the ectodermal cells to become neuroectoderm. And so where does that come from here? I think we're back in Xenopus. Yeah, we're back in Xenopus. So this comes out during gastrulation. It's a mesodermal tissue, of course. And you know how you've got a ball here, which is your Xenopus embryo. At the end of gastrulation, you've got a long thing. So we've got the notochord being laid down before the whole thing spreads out. So once that notochord gets laid down, it does conversion and extension to lengthen, so it ends up the length of the whole embryo. So as the embryo lengthens, it does that. So here in figure 27, you can see how that C&E happens. The notochord starts out as kind of a flat structure, and then you get that intercalation that happens. The cells slide past each other, and they end up becoming longer. Okay, so that's during the extension period, and then the cells undergo a shape change. Slide 28, where they go from up here become a more tall structure. So you can see you've got it 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5 cells high here. And that involves the cells themselves changing shape. And then we move on to slide 29. Once they do that, the cells change shape again. I think we're still extending, because here you can see we've got 1, 2, 3, 4, 5, 6, 7, 8 cells, and here we're down to 4 cells. So I think they're still kind of intercalating and extending. So by the end of this process, you've got a circular notochord, and each kind of section is made up of 4 cells, and they have this pizza wedge shape to them. So again, we're talking about this is happening because of cell crawling for the intercalation, conversion, extension, and it's also change of the cell shape, which is typically because of contraction of the either the apical surface or the other surface that kind of changes the shape of a cell and makes it more of a wedge. And that's about it. So notochord starts out, and then it intercalates, converges, and extends, and then it rounds up by cell change to make that tubular notochord. By the way, I don't know if you're familiar with 80s slang, but tubular used to mean good. That was slang for good. Really tubular, man. That's the 80s. I wasn't alive then. I wasn't born until like 92, I think. But I've heard, I've seen a lot of movies. Okay, so neurulation. Everyone good on notochord? Brian Perez still awake? Thank you, Adelina. Thank you. Yes, yes. I was a prodigy. I've disappointed a lot of people since then. Okay. Brian's awake and life is good. Sydney Snow is happy, and that's all that matters to me. Let's move on to neurulation. Okay, so neurulation I think I find more interesting than the last one, than the notochord changes. So neurulation starts out, it's just ectodermal cells on top, and then you get this notochord. And the notochord then induces these cells to become neuroectoderm. And then you get the whole, your book goes over it again, and it's almost in every chapter. You go from neural plate to neural groove to neural tube. So why is that happening? How does that shape change happen? Well, it starts out down here at the floor here of the neural tube. These cells have got an apical constriction. So you go from columnar cells to wedge-shaped cells. And you get a bunch of wedges together, that forms a circle, or a hemicircle anyway, half a circle. So you can see here in slide 30, these cells at the bottom change shape. Their apical surface contracts and the basolateral does not, and that starts these neural folds going up. So that causes the neural, what am I doing? I don't know. Neural folds go up, and now you got a neural groove. Okay, now once you got the neural groove, you get a second change in shape here. Another apical surface contraction, making wedge-shaped cells here at the dorsolateral port. So previously we made the medial hinge, remember that word, medial hinge, and now we're making dorsolateral hinges that are cranking. So you go from grooves to cranking it around, so now they're starting to touch, getting closer to touching here. Okay. And then now we're going to get to cell crawling again. Once those two sides come together, you can see the surface ectoderm is putting out lamellipodia, and these lamellipodia kind of bump into each other, and then the cells fuse together after that. And it's not explained in much detail how actually that happens. It just says that the lamellipodia interdigate between the two sides and then fuse that together. So now you've got ectoderm on top, and then now the ectoderm lets go of the cells they were connected to. So let's back up one. See here, you've got surface ectoderm that are connected to these neural tissue, to this neural ectoderm. So you've got, adherens junctions between them that are holding them together, and those adherent junctions cause, when the neuroectoderm contract, it does not really contracting, but when it bends like this, it pulls that surface ectoderm with it. And then once it touches, they interdigate with each other, and then they let go. Oop, too far. Okay, so once they do interdigate like that, then the surface ectoderm stops expressing the cadherins that were attaching them to the neural thing, and they start expressing E-cadherin, E meaning epidermal. So the E-cadherins then bind to each other. The cells with E-cadherin bind to each other, and now you've got a sheet of epidermis on top of the embryo. And the same thing happens with your neural tube. They let go of the adherens junctions that were attaching to the epidermis, and they start expressing NCAM and NCADherin, so neural cell adhesion molecules. And then they grab each other, and now you've got the neural tube fused to itself. It's let go of the epidermis, so now you've got a space up there. And then, of course, like we talked about before, that top part of the neural tube will become neural crest cells, and they go epidermal to mesenchymal, and they crawl away laterally, and they set up the autonomic nervous system, parts of the face, and all that kind of stuff. Okay, so that's all I have for neurulation. Basically, it's all about cell shape changes here. First, you've got your medial hinge that wedges up and causes a neural groove, and then you've got your dorsolateral hinges that bring the sides of the neural folds together, and then you've got lamellipodia that fuse them together at the top, and now you've got yourself a neural tube. If it works right, right? And the book says, it's a very complicated process. Sometimes it doesn't close, and if the neural tube doesn't close, typically that's an aborted embryo. Children can be born without neural tube closure, and that's called neural tube defects. You can see a series of them here on slide 33. I suggest going by this one pretty quickly. It's kind of gross. But, they're all somewhat debilitating, but some are worse than others. Okay, so moving on to, okay, so then my last two slides here, 34 and 35, I found this on the internet somewhere. Oh, this slide player. Actually, if you want to learn more about this morphogenesis, look at that slide player. It's not just these two slides, it's a whole lot of slides. So you might want to look through that. It's pretty interesting. So what are the four different movements that happen for morphogenesis? One is migration or cell crawling, which we've talked about. Cell crawling is when the lamellipodium goes out, new integrins grab onto the extracellular matrix there. The cell body pulls itself forward and it lets go at the rear, and then it puts another lamellipodium out. So that's cell crawling. Integrins are really important for the cell crawling motion. And remember, when it's crawling, it's let go of its cadherins, so you don't have adherens junctions anymore. Intercalation, we've talked about this several times. You've got cells that are just sliding past each other, and that causes your convergence and extension. And you've got two different types, the lateral intercalation, which happens whenever you're getting a longer structure, like that notochord we talked about today, that was convergence and extension. The primitive streak was that intercalation type. What did we talk about Monday that was intercalation? Oh God, mind is wiped, mind wiped. What did we do Monday? Let's back up. Oh, Xenobus. Oh, my Xenobus. Okay, so there's intercalation. Oh, right, with the mesoderm coming in through the blastopore. That's also a form of lateral intercalation. And then with Xenobus, we also talked about epibole, and I said radial intercalation. That's what radial intercalation is. You've got several layers of tissue cells in a tissue, and they intercalate and become fewer cells in the cell layers, but more surface area. Okay, intercalation. I like that word. Let me say it one more time. Intercalation. Okay, so ingression. Here you can see cells undergoing that EMT transition here. EMT transition, that's kind of like saying ATM machine, right? So they're undergoing EMT. The cells change shape, they let go of their neighbors, and then they crawl. And that has to do with your cadherens junctions that are being let go of. And then shape changes. This is the other thing we talked about quite a bit in this chapter, which is usually it's actin myosin, usually it's at the apical surface. So you've got this kind of square looking cell, and the apical surface does this, and now you've got a wedge-shaped cell. And we saw that today in neurulation, and it happens in several other places. The bottle cells are formed that way in Xenobus gastrulation. Okay, I hate to say it, but I don't think I have anything left to teach you people. I know I'd love to talk more to you. I'd like to see your faces. Can we see some faces here? Anyone be willing to put their video on? Or are you all naked out there? Oh, there's Adelina. Hello, Adelina. Let's go to, oh, no. Brian Perez, I knew I could count on you. Brian needs a haircut. Almost as bad as me. There's Leo Lee. Let's bring up Sydney Snow. Let's see the snow person. No, she's not going to do it. There's Adelina. Okay, can we? Austrian Gravel, Nick Mather. You're not going to show me your faces, eh? We're done? There's Rachel Siller. That's a nice hat. I like the hat, Siller. Are you Italian? Yeah, okay, good, good. I'm Irish. You can see how bald I am. That's an Irish trait. Nobody else wants to say hello? Julia, Keegan, Cyan. Not showing my face. Sydney says no. Just shave. Oh, Nick just shaved his head. Oh, you're lying. You're lying. I was thinking about shaving the sides, and then I realized they wouldn't have anything left. So I don't know. I'm still thinking maybe the comb over. Another month. you think? And then I could like swoop it around like our fearless leader in the White House. Who is this? Who is this? I only see eyes. Oh, that must be Justin. Justin Drusis on his iPhone. Yay, Justin. Okay, well, I got nothing else here, people. So we've got our final next week, which will just be the fourth exam, really, not a real final. Any questions about the class in general? Maybe I'll try and get a couple practice questions up this weekend. Why don't I do that? Tomorrow morning, I'll put some practice questions up you can look at. And then we'll have our final, which will be an hour and 15 minutes long. And then we'll call it a day, I guess. I think everyone's doing pretty well in this class. I have a hard time grading harshly in a class that is not normal like this. It's kind of hard. But I think everyone's doing really well. All right. Well, I'm babbling and babbling, and I'm just going to stop babbling now. So I'm going to close this and going to get some thumbs up on closing, saying goodnight. Say goodnight, Gracie. Good night, Gracie. Okay, good. All right. See you later, guys. Ending the meeting. Bye-bye.